So here's the second part to a review of equilibrium acids and bases. If you are following along with me, you might want your data booklet out. There's especially lots of references to the indicator page, which is page 10. So taking a look at this first one, we have some information about a reaction we used in baking. So we could read this through, and then some information about lactic acid and giving us a Ka. That Ka is implying that it is a weak acid, because if we did place it on the data booklet, it would be below the gray line on page 8 and 9. So when it's asking the net ionic equation for this dough rising, we would want to pick our strongest acid with our strongest base. So here this would dissociate into Na positive and HCO3 negative, and it will be our strongest base, where our lactic acid will be our strongest acid. So the reaction that shows our strongest base with our strongest acid, I believe, is D, and it does go a little bit more into detail. So this does look a little bit similar to just a few of the other ones, but why it's not completely what you might have predicted, it's when our acid donates hydrogen to the base, we make H2CO3. Now, this carbonic acid is something that decomposes very quickly into carbon dioxide and water, and it does tell you that in your data booklet as well when you look at carbonic acid. So instead of writing H2CO3, they are showing it decomposed, and this gas here is what's causing that bread to rise. So that's that first part. Now moving on to some calculations. Asking for the concentration, because you have a weak acid, we are dealing with the Ka, and your Ka will be the hydronium ion concentration squared divided by your weak acid. And this is minus hydronium, but because we're looking for it, we could ignore it in the denominator. So we'll plug in those values. We have the Ka value from the information given, so 1.4 times 10 to the negative 4. It's taking a while here. There we go. And that's going to equal our hydronium concentration, which we're trying to find. And this is squared. It's a bit of a by 0.20 moles per liter. So we're just solving for hydronium. So we'll multiply that weak acid up and then take the square root of the whole thing. And when we do that, we'll see that our answer is going to be B. Okay. The next part, just waiting for this to catch up to me here. So our next part, looking at what we had there, it's asking you for your answer for multiple choice 26 to figure out the pH of your system. So when I'm looking at this here, let's see if this will work for me. If not, I'll start over. Okay. Let's see. I think it will be okay. So to do that, we're just going to normally finding the pH using that formula. You just take the negative log of your hydronium concentration, which we have solved for. And so when you do that, you will get the answer is 2.28. And then just clarifying 3 digits. Digits are your numbers, so you'd still do include your decimal. So if you're filling this in, it would be 2.28. Okay, looking at question number 27, now we're doing the reaction, and it's asking about the number of number of protons donated. With this question, why it does get a little bit confusing, it's not giving us what the acid is, but we are given enough information to set up a ratio. So for every 50 milliliters of the acid, we need 150 milliliters of the base to react. So that would be a 1:3 ratio. So the number of protons donated would have to be 3 to completely react with our base. So that's definitely a bit of a tricky question, because it's relying on the ratios, and it's a little bit more Chem 20, which you don't see that often. Moving on to question 28, and also I didn't love that this question was in this section, because this is actually a redox question. So it brings us a little back to our last electrochem unit, and when you're doing this, you do want to take a look at what's reacting. And you probably did this reaction in a lab, because it is a very common one asked in Chem 30, where you have acidified H2O2 and KMnO4. Now you'd want to find your strongest OA, and that would be the MnO4 with MnO4 negative with the hydrogen ions, and we would write out that full reaction based on page 7 of your data booklet. Then your strongest Ra would be the H2O2, and same idea, you would have to write out that reaction in your data booklet. Then to balance things out, we would multiply the first one by 2 and the second one by 5, and then cancel what we can. So if we did this completely correct, you would see your answer is D. It's similar to A, except what it's missing is that your hydrogens end up canceling on the product side if you wrote this all out. So I wasn't going to go into too much detail just because this is more electrochem, but definitely I could do another video focusing on this question and writing it out a little bit more. Now, once you have your balanced chemical equation, then we can go to question number 9 of your numerical response, and that is now to do the stoic part, the math. So even when you're taking a look at this and you're looking at the colors, you can tell that that first one is not within the range, but you can double check that. And if you wrote down all of the values, that first one you had 17 point something, and then it was 16.3, 16.4, I'm sorry, that would be 5, and the last one was 16.4. So this question asking about the volume of permanganate for the calculations, we're not going to use the first one because there's an error. So we'll add up the other 3 and divide by 3 and get that average, and it's 16.4. Once you have your average volume, now in the next part, it's asking the concentration. So going to this reaction, and if you're just setting it up, you have 16.4 milliliters. You want to turn that into liters by dividing it by 1,000. So 1 liter has 1,000 milliliters. That will get you to liters of the MnO4. Then you can multiply that by the concentration of the MnO4, which was given 0.15 moles per liter. And now that we have moles of MnO4 negative, you can turn that into moles of your unknown. So we'll have 2 moles of KMnO4 on the bottom and 5 moles of H2O2 in the numerator. And then lastly, you want to divide by what we're titrating by, and that was 0.02, which was your 20 liters per trial. Now you plug that all into your calculator, and in this question it is asking again for that 3-digit number. That will be 0.31, and your digits are just your values, so the digits would be the 0, 3, and 1, and if you're filling this in, you still want to include your decimal. Okay, moving on to this next one, we have some information about an acid, and we are given the Ka value. Now that matters. This Ka value, again, if you put this on the table, you will see that it is a weak acid. And weak acids, when you have your reaction, when you react it with water, and this would be liquid water, it is in equilibrium, and the hydrogen is going to go over to the water to produce hydronium, and then you will end up with your negative ion, so N3 negative. Now with the water there, everything is balanced, but when you do put it into your equilibrium expression, and these two would be AQ, we would not include the liquid water because we don't include pure liquids in the expression, and then you do products over reactants, and I believe that one makes your answer as B. The other part here is, again, this is a common question where it is asking to compare your reactants in your products. Because you have a weak acid, you have very, very little amount of products being formed. Less than 1% is the value I usually say, but it's very, very small. So you have a lot of the reactants, very little products. So when it's asking you to compare, the one that works here is B. Your concentration of your acid is going to be greater than the concentration of the hydronium ion. Looking at number 11, asking us to find the pH, we got to use that Ka formula once again, right? You have your hydronium ion concentration squared divided by your weak acid, and we could ignore the hydronium in the denominator because we're finding it. So we are going to plug in your Ka value, you're going to plug in the weak acid and solve for hydronium once more. Once you have hydronium, then we will take the negative log of the hydronium's concentration, plug it into our formula, and keeping 2 significant digits, you'll see your value is 2.64. And because this is a pH, this is showing 2 sig digs because it's only your digits after the decimal that are significant. This next part is now showing that we're neutralizing your acid with a base. So we want to set up that reaction. So you would write out this reaction, so that NaOH. And reminder, when you are looking at like the stoic reactions, you don't need Bronston and Lowry. You just write out the reaction like you would when you took Chem 20. So when this comes together, you're going to have the Na coming together with the Na with the nitrogen. This is an odd reaction. And then we end up having, and I'm sorry, I just want to double check this. We would have H. All right, okay. And then we have water still here. So I wrote it down wrong the first time when I went through this. So once we have this all figured out and we see that we have that 1-to-1 ratio between our acid and our base, what we want to do is then set up our information here. I just want to make sure I have it there. Divided by 6. Oh, okay, there's a 6. Okay, never mind. I'm sorry about that. Let me go a little bit faster now. So I have kilograms of our acid. I will need to turn that into grams by multiplying it by 1,000. And then I would have to use the molar mass of HNO3, which is 1 mole contains 43.04 grams. So far up to here, I can see my units canceling, and now I'm at the moles of the acid. From the moles of the acid, I want to now turn that into moles of the base. So that will just be that 1 mole of the base over 1 mole of the acid. And then I can use that concentration. I want liters on the top and our moles in the denominator. Plug that all in, and I will see my answer here is 8.52 liters. Okay, our next one, we have some information about a buffer. And here it's just knowing the definition. So the function of a buffer is to maintain a constant pH when a small amount of acid or base is added. Now, this question number 32 is asking about what buffer is present in our blood or one of the systems. And hopefully we did see this in our lessons, and that's going to be the one with H2CO3. Now, you could rule out these ones because we never would have anything strong, but it would be a little bit harder to figure out between these two. So just remembering that the one with H2CO3, that is a buffer system within our blood. Question number 13 is just matching based on the forward reaction. So if we're looking at our reaction and we're looking at the products just to help us, we would see that the hydrogen from the HSO4 negative went over and donated to the HCOO negative. So because that hydrogen is leaving, so noticing that this doesn't have a hydrogen, that would be our proton donor, and then that would be number 2, our proton acceptor. So when we're going through this, your acid is number 1, its conjugate base would be number 4, the base is number 2, and the conjugate acid would be number 3. So I know I'm writing it in this order because it is asking about the forward reaction. So start with your reactants and go to your products. Question number 33, asking for a conjugate acid-base pair. Here we're just seeing what would line up and match, and that would be the ones with H2BO3 negative, which is B. So again, you can look at the other ones. To be related, you have to be the difference between one hydrogen. So definitely not A, definitely not C, and definitely not D. So the other options weren't even that distracting. The only option here was B. Asking for the amphiprotic species. The reminder to be amphiprotic, you're either water or you have a hydrogen and a negative charge, right? Hydrogens can donate, negatives can accept. So the only one that's doing that in this reaction would be A. Question number 35 is definitely using our indicator information. So you might want to look at your indicator page to help you here. And to start off with, it's asking about the pH of rainwater, and then it's being tested. So methyl red being yellow, if you look at your indicator page, that means your solution has to be greater than a pH of 6. Phenol red being yellow, looking at your indicator page, it means your pH has to be less than 6.6. For bromocresol green, we have to be greater than 5.4, but we also know we're greater than 6, so that really doesn't tell us too much. Phenolphthalein being colorless means you're less than 8.2. Same idea, we know we're less than 6.6, so that's not really telling us too much. So in bromothymol blue, what we can get from here is that our pH is somewhere between 6 and 6.6. And if that is the case, then what color would we be? So in bromothymol blue, that pH is going from 6.0 to 7.6, and anything below 6 is yellow, anything above 7.6 is blue. Now I found this a little bit tricky because I would have assumed that we would see the color green, because if we're right in between here, we should be more of a green color, but then green wasn't an option. So because when you're looking at the number 6 to 6.6, that would be closer on the 6 side, then I would just go with that color being more yellow. And the one that satisfies that would be C. All right. So this one is just showing that you know how to read a graph. If we wanted an indicator for this titration, we need to realize that our equivalence point is that halfway point when it drops. So I would look for about a halfway point, and for me, my estimate would be around 6 here, depending on how accurate I am with my estimate. And then I would look at my options, and the best one here would be C, with having 6 within the range. 37, looking about the pH being around, POH being around 3.2. If you find POH hard to deal with, turn it into pH, because I find students always understand pH better than POH, just because it's that opposite way of thinking. So if you are a pH of 10.6 or 10.8, sorry, you definitely know that you are a base. And if you are a base, you're definitely not a proton donor. You're not going to react with zinc, because that would be an acid would do that. And then looking at your possible color changes, C is the only one that works out. D does not work. So you're just looking at your indicator page and seeing which indicator would fit that information. Now I'm finding that these questions are starting to get very repetitive, which is a good sign, because then you know these are the type of questions to expect to see. So this one, numerical response 14, it is telling you information about where you are to get to your second equivalence point. So that part matters a little bit more for question 38, and we'll get there in a moment. So with your first equivalence point, or not your equivalence point, your titration, when your titration ended, it's just finding that average volume. So once again, we are looking, the first one gives us 12.1, and then we have 11.3, 11.4, and 11.2. So we're not going to include the first one because it's out of range, and then we'll take the average by adding the other 3 up and dividing by 3, and you'll see your average volume is 11.3. Now, this part does get a little tricky. Your reacting H3PO4 with any OH. So we could use a little bit of Bronston-Lowry here to see what's happening. And we have one hydrogen moving over. And when that happens, you will get H2PO4 negative and water. Now, that's what's going to be reacting at your second equivalence point. So H2PO4, you're still adding in that OH ion. And when this one reacts, going over, you are producing HPO4 negative 2 and water. Now, if you go to balance out our reaction here, this is actually a 1 to 2 ratio. And we would know that with our NaOH in there. I just won't write that all out again. But that is allowing us to see that we have 2 hydrogens for our OH. So when you go to fill this out, you definitely will need your average volume. So 0.113, and then, oh, sorry, there should be an extra 0 in here. And then you're going to multiply this by your concentration of the NaOH. But instead of going to multiply by a 1-to-3 ratio, it's going to be a 1-to-2 ratio. And that is, again, because we're looking at that second equivalence point, not that first one. And then we're going to divide by the amount of our acid that was used, and when we do all of that, we'll get our answer in moles per liter. It's a very small value, so we'll multiply it by 1,000 to see that our answer is 70.6 millimoles per liter. Okay, so this next one is again about a buffer system, and in this question, I like these. I think these buffer questions are nice and easy. So within this, we have our acid part of the buffer and you have the base part of the buffer. If you're adding in hydronium ions to your buffer system, it is going to react with the base part of your buffer. So that's what we want to take a look at, which reaction supports that. So when we do see that, your answer here is B, hydronium being added to the base part of the buffer. Hydroniums will donate a hydrogen and we will end up neutralizing a little bit of that acid like a buffer would. So our next question here is another titration question. This time we have NaOH reacting with HCl, so that is a 1-to-1 ratio. So this one is overall, I think, pretty simple in terms of figuring it out. So 10 mils, let's change that into liters, so 0.01 liters, multiply it by your base, so 2.57 moles per liter. Again, if you write out this reaction between NaOH and HCl, it is a 1-to-1 ratio. So then your last step is then just to divide by, we're finding mils. Your last step, because that will bring us to moles of your base over, this would be moles of your acid. I should probably use some more units in here. So this one was my base. So now that I want liters or milliliters to end, instead of multiplying by my concentration, I want to divide. So I'm going to put 1 liter in the top and 0.860 moles in the bottom so that I can see moles canceling. Then I'm left with liters, but then I'll need to turn that into milliliters because it's a small value. So I multiply by 1,000 and you'll get 29.9. Now, in question number 4, asking about which equivalence point or which indicator would identify this equivalence point. You are reacting a strong acid with a strong base. Your equivalence point should happen around the pH of 7, and usually with that strong acid, strong base titration, we're using bromoethyl blue, so we can also narrow it down based on the indicator page. Our next one, this one gets, I think, a little bit tricky here. Question number 16. This is talking about the drops instead of giving us a volume. So we have a ratio that we can figure out in terms of how much of the acid we need compared to the base. Overall, I'm not a huge fan of this question. I think I'll come back to it if we have a little bit more time, but we just have to come up with that ratio about how many drops we need to neutralize, and that would be your mole ratio. And then from your mole ratio, you would be able to figure out the concentration of HCl. Question 41 is now asking us to analyze Le Chat. And in this one, our goal is between these two steps, we want to make more sulfur so that we can remove it. So when it's asking how can we remove the amount of sulfur or increase the amount of sulfur removed, what could make more of it? So adding a catalyst will do nothing to a system in equilibrium. Removing water vapor is going to be the answer, and that's because if you decrease it, we would shift to the right to replace it, and that would also make more of your product. C threw me off a little bit because if you did increase the volume, you move to the side with more moles. The reason why that threw me off is I forgot to recognize that this is a solid coming out, so we actually would not include it in equilibrium. So this side does actually not have more moles, it has less because we're not including the solid. So that would actually cause a shift to the left, not a shift to the right. And then the increasing the temperature of the system. If I wasn't confident about B, I probably would use Hess's law short to figure out that temperature. But I also believe it tells you that you're adding in heat somewhere, or maybe I just know that. Anyway, so we do know the answer here definitely is B. That is what would cause the shift. The next one, 42, an indicator that can identify a solution between the pH of 4 and 4.3. Again, you're just looking at your indicators page, making sure you understand how to read an indicator, and the one that would work out is B-methyl orange, which would include that range. Question number 17, another titration question. So again, this is getting very familiar. So just like the other ones, in the end, you wouldn't include the first volume. You'd figure out the other three and see that the average volume is 6.51. And then when you're actually doing your calculation, you would take your average volume and turn it into liters. So your 6.51 milliliters. And actually, I did use my unrounded value from my first calculation. So that would be milliliters, and I want to multiply this by 1 liter over 1,000 milliliters. So now I have my volume of the NaOH. Now I can multiply it by the concentration, which is 5 millimoles per 1 liter. So now liters cancel, and I'm at my concentration of the base. This is a 1-to-1 ratio, so multiply it just to change our moles from moles of the base to moles of the acid. And then lastly, I want to divide by the volume used, and I had 10 mils in each sample, so turning that into liters would be 0.01. Multiply that, put it into your calculator, and you should see your answer is 3.26. Also noting, I did not change my millimoles to moles for this, just because in my calculation I had millimoles and in my answer I had millimoles. So if I did convert it to moles, I'd have to convert it back again to millimoles, which would be just essentially changing your units back and forth twice, working out to the same answer. Question number 43 is another one about NaOH being added to our system. If NaOH was added, because you can't see it directly added, so we can split it up into its ions. We don't see it directly added, so instead it's what can you take out of the system. So H3O and OH negative will come out of the system as water, and ended up being 2 water molecules as a liquid. And if that is removed from the system, you would be shifting to the right to replace it. So if we shift to the right, that means we have more of the Bb negative ion, which would be more of a blue color. The other part is if you're decreasing your hydronium from the system, right? So if you take a look at your pH scale, you're decreasing hydronium means you're becoming less acidic. So if you're less acidic, you're moving away from your acid, you're increasing on the pH scale. So your answer is B. And this second last one here, I did find it a little bit confusing just reading over it. It's talking about a thermometric titration, and this is a little bit of inference where we have to see that this point here is the point where your titration would be over. So when we're doing this one, as long as we make that connection, then this question's not that hard, and we can find the concentration. So we would do what we would do before, get to moles. So 20 mils divided by 1,000, multiply it by 0.2, multiply it by your ratio, and then divide by your volume. The volume you want to use is the volume at that point that before it drops. So if you did that all correctly, you would see your value here is 0.13. And again, I feel like it was a bit of inference, but it was a bit obvious, and I think there probably would have been a bit more information. And as you can kind of tell by the graph, this is a very old diploma question. One more about a buffer. So looking at your buffer here, you have your acid part of the buffer, you have your base part of the buffer, and then it's asking what would happen if you're adding hydronium ions. So just like the other one, if you add in hydronium, it's going to react with the base part of your buffer to get neutralized. So we would see the answer for this one has to be D. This very last question, and if you've been with me this far, thank you for that. But this very last question is, oh wait, I think I skipped one. sorry. Nope, I had two more. So this question here, I do like this question because I feel like it's a way for you to understand page 8, 9 of your data booklet, as long as you understand what's being favored. So within this question, you would notice that we have an acid and a base. Right? We know that this is the acid because it's donating a hydrogen. We can tell by the products, and the base is accepting. If products are favored, if you put this on your table, your acid has to be higher on your table than your base. So I was just starting when I did this question, not writing everything out, but if I know I have acids on my left and bases on my right, then my acid has to be higher than the base that's reacting. So that's the first part I put in. Now I skipped the second part, or the second reaction, just because it doesn't relate to what I had. So I just go to my third reaction. It says reactants are favored. If reactants are favored, your base is higher up than your acid. So my base is here. I already have it placed. It has to be higher on the table than my acid. So now I've placed the acid. Now I can go back to the next one. Again, telling me products are favored. My acid has to be higher than the base. The acid's already placed. So my base would be OBr negative. Now when it's asking about the strength, that HNO2 would be the strongest one. Next would be the acid that corresponds to this base, which would be formic acid, so number 1. Then HN3, so number 2. And then lastly, the acid that relates to this base, which would be number 3. Okay, and now the very last one, taking a look at here, and it's asking to identify what indicator you can use at the second equivalence point. So this one, just recognizing here's your first equivalence point, here's your second equivalence point, coming over to read the pH around that point and seeing which would work out the best. And I believe here your answer is A for phenolphthalein. So as always, I hope you found this helpful. If you did, please subscribe. If there's any other question I could do for you, or look at another one within here in a little bit more detail, because I know I was going pretty fast, just let me know. As always, thank you for watching. Bye.